So what if I told you that the whole idea for the GPS in your phone was dreamed up in a story written before the telephone was even a thing? It's pretty wild, right? Today, we're going to dive into the incredible world of satellite communications. This is the invisible network that powers, well, basically everything in our modern lives, from weather forecasts to, yeah, the very device you're probably watching this on right now. All right, let's get into it. Yeah, believe it or not, the very first idea of an artificial satellite, it didn't come from some high-tech lab. Nope, it actually showed up in a story, a sci-fi story called Brick Moon by Edward Everett Hale, all the way back in 1869. I mean, think about that. While the rest of the world was just getting their minds around telegrams, this guy, Hale, was already dreaming up navigation and communication hubs floating way up in the sky. So this timeline, it really shows you that incredible journey from pure fiction to hard fact. It all kicks off with Hale's story, right? But then you've got this Russian scientist, Konstantin Tsiolkovsky, who comes along and gives us the actual math to get to space. His rocket equation was the scientific key. And then fast forward to 1945, and the legend himself, Arthur C. Clarke, lays out the exact blueprint for the global system we literally use today. And the thing about Clarke's idea, it's just so elegant, it's stunning. He did the math. He figured out that at this one very specific altitude, we're talking about 36,000 kilometers up, a satellite's speed would perfectly match the Earth's rotation. So what does that mean for us down here on the ground? It means the satellite would look like it's just hanging there, totally motionless in the sky. And the kicker? You'd only need 3 of them to connect the entire planet, just 3. It was absolutely brilliant. Okay, so we've got this incredible theory. It's genius, but how do you actually make it happen? How do you turn that into reality? Well, the answer, as it so often is, comes down to a rivalry. In this case, one of the most intense rivalries of the 20th century, the Cold War, and the space race it ignited. But hold on, before we get into all that drama, let's just make sure we're on the same page. What is a communication satellite? Think of it like this. It's basically a relay station in space. That's it. It's not creating any information itself. It just catches a signal from one spot on Earth, juices it up with a power boost, and then beams it right back down to another spot. October 4th, 1957. You're going to want to remember that date. This is the moment that changed everything. The Soviet Union launches Sputnik 1. It's just a 184-pound metal ball, just beeping this simple little radio signal, but it sent absolute shockwaves across the entire globe. And just like that, the space race wasn't just an idea anymore. It was on. Sputnik's launch, it wasn't just some single breakthrough. It was really a perfect storm, a convergence of all these powerful new technologies coming together at the same time. You had the high-powered rockets to get there, you had the brand new tiny transistors to build smaller electronics, and you had solar cells to keep the whole thing powered up. And of course, all of this was being supercharged by intense military interest and that fierce international rivalry. Now, here's a really crucial distinction to understand. The very first satellites, they were basically just giant mirrors in space. We call them passive satellites. All they could do was reflect a signal back down to Earth. And what that meant was you needed these massive, like city-sized ground stations to basically shout a signal loud enough for it to bounce back. The real game changer, that was the active satellite. This is the one that's more like that cell tower in the sky. It doesn't just reflect the signal, it actually boosts it itself before sending it back down. Huge difference. And this right here shows you exactly how that works. It's pretty cool. So a ground station shoots a signal up to the satellite. We call that the uplink. Then the satellite's transponder, its little brain, catches that signal, gives it a power boost, and then beams it back down to a totally different spot on Earth. And that's the downlink. Uplink, downlink. So simple, right? But absolutely revolutionary. 1963. This is the year. This is when Arthur C. Clarke's incredible vision finally became a reality. NASA launched SYNCOM, and it proved that Clarke's idea, it wasn't just some wild science fiction story anymore. No, it was the future of global communication. All right, so we've got the satellites, we know how they work, but where do you put them? I mean, it's not like you can just fling them up there and hope for the best. They have to travel on these invisible highways in the sky that we call orbits. And each one of these highways has its own set of rules, its own speed limit, and its own special purpose. Now, the physics here can get pretty complicated, but really, it all boils down to one simple rule. Just think about swinging a ball on a string, right? The longer that string is, the slower the ball goes around in a circle. It's exactly the same with satellites. The higher up they are, the farther they are from Earth, the slower their journey around the planet is. And believe it or not, that one simple principle is the absolute key to designing every single satellite network out there. And it's not just about the altitude, how high it is. The path it takes is also super important. A satellite can orbit right over the equator, or on a tilted, inclined path, or it can go right over the North and South poles. That polar orbit, for example, is perfect if you want to map the Earth or, do a little spying. Because as the planet rotates underneath it, the satellite eventually gets a good look at pretty much everything. Okay, so now that we've got the basics down, let's talk about the three main orbital highways in the sky. And let's see how they power the technology you and I use every single day. We're talking about LEO, MEO, and GEO. So let's start with the big one, GEO, or geostationary orbit. This is the orbit that Arthur C. Clarke first dreamed up. At that magic altitude, 35,786 kilometers up, the satellites are moving in perfect sync with the Earth's spin, which means, from our point of view, they look like they're just hovering in one fixed spot in the sky. It's actually why your satellite TV dish can just be pointed in one direction and you never have to mess with it. Now, the biggest pro for GEO is its huge coverage area. It's massive. But the big con? It's that distance. It takes about half a second for a signal to make that round trip, all the way up and all the way back down. And that delay, what we call latency, is exactly why GEO is terrible for things like fast-paced online gaming or even a video call. You would absolutely feel that lag. Okay, let's come a little closer to home now. We're moving down to medium Earth orbit, or MEO. You can think of this as the just right orbit, the sweet spot for navigation. This is where the GPS constellation lives, that whole network of 24 satellites all working together in a beautiful cosmic dance to tell you exactly where you are on the planet. So MEO is kind of like the best of both worlds. The signal delay, that latency, is way lower than GEO, and you get much better global coverage, especially over the poles. But there's always a trade-off, right? You need more satellites to get that full coverage, and the signal from them isn't quite as beefy as what you get in our next orbit, which is low Earth orbit, or LEO. This is the final stop on our tour. Now, you should think of LEO as a super crowded, super high-speed highway that's just a few hundred kilometers above our heads. The satellites here are just whizzing around the Earth, and they have to work together in these massive swarms, these mega constellations, to give us that continuous, seamless coverage. The huge, massive advantage of LEO is speed. Pure and simple. Because they're so close to us, there's almost zero signal delay. It makes it perfect for things that need to be super responsive, like satellite internet or crystal clear satellite phone calls. But here's the catch. You need a ton of them. We're talking hundreds, even thousands to get that global coverage. And because they're so low, there's just enough atmospheric drag to slow them down over time, which means they have a much shorter lifespan. Okay, so let's wrap this part up. It's actually pretty simple when you break it down. GEO, way up high, that's for broadcasting things like TV and watching weather patterns. MEO, the middle ground, that's for your GPS navigation in your car and on your phone. And LEO, down low and fast, that's for speedy connections like satellite internet. 3 different highways in the sky, 3 totally different jobs, all working to power our world. But, the story of satellite communication is nowhere near finished. In fact, it's probably evolving faster right now than it ever has before. And what's driving it? Our own relentless, nonstop demand for more data and constant everywhere connectivity. So what's on the horizon? Well, for one, satellites are getting way smarter. They've got powerful computers on board now that can process data right there in orbit. They're also getting bigger antennas, more powerful ones, to deliver those lightning-fast speeds we all crave. Really, it all comes down to one thing: trying to quench our world's absolutely insatiable thirst for more and more bandwidth. So think about it. We went from one single fictional brick moon in a story to literally thousands of real satellites blanketing our planet right now. This technology has fundamentally rewired the way we live. There's no question about it. And as our skies get even more crowded with these orbiting supercomputers, the real question we have to ask ourselves is, how are they going to continue to reshape our lives, our connections, and our entire world down here on the ground?